Find the limit if it exists. In our first example, we have the limit as x approaches 6 from the right. This fraction can be reduced by factoring the denominator into x plus 6, x minus 6. Cancel your x minus 6's. That reduces your fraction to 1 over x plus 6. You can safely plug in 6 to get an overall limit value of 1/12. In the example below, we have the limit as x approaches 0 from the left side, superscript negative, absolute value of x over x. Excuse me. Absolute value function is piecewise. It's defined as x as long as x is greater than or equal to 0. It's defined as negative x if x's are negative. Since we're approaching 0 from the left side, those are values of x that are negative. Replace your numerator with the definition of absolute value of x. When their x's are negative, that's negative x over x, which is negative 1. That's a fixed constant value, so your limit value is negative 1. Find the limit if it exists. This time we have a piecewise function. We're looking for the limit as x approaches 2 from the left for this particular function. The top piece, x plus 9 over 9, is defined as long as your x value is less than or equal to 2. The bottom piece is used for x is greater than 2. Since we are approaching 2 from the left, we're going to use the top piece because it's designated for x values that are less than or equal to 2, which can be found left of 2. As we approach 2 from the left, we can safely substitute 2 in for our x value. So below, limit as x approaches 2 from the left, x plus 9 over 9, replace x with 2, and that gives you a limit value of 11/9. The limit as x approaches 5 for f of x. This is also a piecewise function. Because we don't have a superscript with our 5, we're going to approach from the left and the right. The top piece of this function is good for values of x less than 5. The bottom piece of the function is good for x's that are 5 or larger. As we approach 5 from the left, we have to use the top piece. Substituting 5 in, we're going to get 25 minus 20 plus 6 for a total of 11. Approaching x from the right, we use the bottom piece because those are values of x that are greater than 5 or to the right of 5 on a number line. Replace all your x's with 5. Be careful not to include the negative in your calculation here. That's a negative 25 plus 20 minus 2 is negative 7. Since our limit is not the same approaching from the left or the right, this limit does not exist. We do not have a head-on collision because the function values are different. Discuss the continuity of the function. We have the function f of x equals 1 over x squared minus 16. The denominator is a difference of 2 squares. We can factor that as x plus 4, x minus 4. Neither factor can be canceled because the numerator is only 1. At the bottom right of your screen, factors in the denominator that cannot be canceled, the zeros of each one, negative 4 and positive 4, are vertical asymptotes. Those are values of x that make the function undefined, and they are non-removable because we have nothing in the top of the fraction to cancel. So this function is not continuous at x equals -4 or +4. That's true for any vertical asymptote. Discuss the continuity of the function. Excuse me. We have a rational function given, x squared minus 9 over x plus 3. Factoring the numerator as a difference of two squares leads to a cancellation of x plus 3. That leaves x minus 3 as the simplified version of the function. However, we have to be mindful that the original denominator is 0 if x is -3. At the bottom right of your screen, I've highlighted -3. When I go to the graph, notice that there's a hole in it. If you can remove a denominator by cancellation, then x plus 3, because we can remove it by canceling, x equals -3 is where a hole will occur. And back up to the top of your screen, that is called a removable discontinuity. It's a hole in the graph. You can have a limit exist at a hole, just not at a vertical asymptote. Discuss the continuity of the function 1 over x squared minus 9 on the interval from -1 to 3. Factoring the denominator, x plus 3, x minus 3. 2 examples ago, we saw that if you cannot cancel a factor in the bottom, then the zeros of those factors will be vertical asymptote locations. So we're going to have vertical asymptotes when x is -3 and +3. In this interval, -3 is not inside of it, so we don't even have to pay attention to that one. +3 is the edge, the right edge of the interval. In your graph, I boxed in the parts of the graph that is going from -1 to 3 with respect to x coordinates, and I highlighted it here in green. From -1 until almost 3, we can't be exactly 3 because of the vertical asymptote. This function is continuous from -1 to almost 3. Parentheses are used to designate close but not exact. A bracket is used for exact. Find the x values at which f is not continuous. Determine whether they are removable. In our first function, we have x over x squared minus x. Factoring an x out of the denominator, we get x times x minus 1. Cancel your x. This x is equal to 0 when x is 0. Since it can be removed by canceling, it's a removable discontinuity. The factor x minus 1 cannot be canceled. It's non-removable. If x is 1, the denominator becomes 0, but it's non-removable if you cannot cancel it. In the second example, we have the function x minus 2 over x squared minus 4. Factoring the denominator, x plus 2 times x minus 2. X minus 2 can be canceled, leaving you with a reduced fraction of 1 over x plus 2. X minus 2 you can remove by canceling, and it has a 0 at x equals 2. The factor that cannot be canceled, x plus 2, it has a 0 when x is -2, and it's non-removable.